Today, I want to look at the area enclosed by a polar curve. But before we go ahead and look at that, let's remember what we did when we were looking for the area under a Cartesian curve. The first time that you met this, you will have seen just some sort of curve, and the question is, how can we find the area under the curve between A and B? We divide up the curve into lots and lots of rectangles, each of width delta x and height y0, y1, y2, etc. And the area under the curve is going to be approximately equal to the area of all these rectangles. And as the width of each rectangle gets smaller and smaller, as delta x tends to 0, the approximation gets better and better. So what we were really doing there was looking at the area of what I will call a typical rectangle. And that is y delta x. So the area of all the rectangles is add up all the y delta x's between x is A and x is B. Then if we let delta x get smaller and smaller and smaller, let delta x tend to 0, sigma A to B y delta x becomes the area under the curve y dx. And that is what you meant, or what you met, when you first met the idea of area under a curve. Sigma y delta x becomes the integral y dx. Well, let's take this idea on to polar curves. When we look at the area enclosed by a polar curve, if we think of moving along the curve from A to B, as we move from A to B, so we are sweeping out the area of this sort of sector OAB. So the first thing that we're looking at is a very different shape. We're no longer looking at something which could be thought of as a whole lot of rectangles down to the x-axis. Instead, we can think of this area as made up of lots and lots and lots of small sort of sectors. It's not quite a sector, because a sector, of course, would have a circle at the end. So let's look first of all at the area of, I will call it a sector, OPQ. If you can remember your theory, the area of a sector is a half r squared times the angle, which is delta theta. So the radius there is r, there's the angle delta theta, a half r squared delta theta. Therefore, the area of OAB, thinking of AB as a curved line, is approximately the sum of all the half r squared delta thetas. Let's think what happens now as delta theta tends to 0. We can think of very, very many strips here. And I've drawn several strips for you in this diagram. So we are now splitting the area, this sort of fan-shaped area, up into all sorts of small sectors. So as delta theta tends to 0, the area of OAB becomes the integral, same way as before, half r squared d theta. From some initial value, whatever the value of theta is at A, to whatever the value of theta is at B. And this is how we're going to work out now the area enclosed by a polar curve. In this example, we're asked to find the area between the curve 1 plus tan theta and the half lines theta equals 0 and theta equals pi by 3. So here we have the curve 1 plus tan theta. The half line theta equals 0 is, of course, the initial line or the x-axis, and the half line theta equals pi by 3 will be that one. And our area is split up into lots and lots of small sort of sectors. It's that I use to help me remember what the formula for the area under a polar curve is. Each sector is a half r squared delta theta. And so the area is the integral from the first value of theta to the last of a half r squared 1 plus tan theta squared d theta. And now we are back to some nice easy algebra. 0 to pi by 3, a half, 1 plus 2 tan theta plus tan squared theta. Let's make that 2 a little bit bigger. D theta. That's the integral from 0 to pi by 3. A half of 2 tan theta is tan theta. And if we look at 1 plus tan squared, 1 plus tan squared is sec squared. So that's plus a half sec squared theta. D theta. Integral of tan theta is log sec theta. Integral of sec squared theta is tan theta, so that gives me a half tan theta. And my limits are 0 to pi by 3. Sec pi by 3, well, cos pi by 3 is a half. Sec pi by 3, therefore, is 2. And tan pi by 3, picturing the triangle, is root 3. So that gives me plus root 3 over 2. Sec 0 is 1 over cos 0, that's 1. Log 1 is 0. And tan 0 is 0. So the area we're looking for is log 2 plus root 3 over 2.